All right, the next example we're going to look at today is, of course, a conventional two vehicles traveling at the same time. We're trying to find the rate at which the distance is changing between them. So let's start out by reading the question here. We have a car traveling north toward an intersection at a rate of 60 kilometers per hour, while a truck is traveling east away from the intersection at a rate of 50 kilometers per hour. Okay, so find the rate of change of the distance between the car and the truck when the car is 3 kilometers south of the intersection and the truck is 4 kilometers east of the intersection. So we are working with direction here. So let's start off by drawing ourselves a little bit of a compass here. Okay. All right. So our origin, where we're starting from, what our reference point is, of course, is our intersection. And so I'm going to denote it as I. So what I'm doing here is, of course, drawing myself a little diagram, a little snapshot is actually of what is actually happening here. So we have a car that's traveling north at a rate of 60 kilometers per hour. So here's my car. It's somewhere down here south, and it's going towards the intersection at a rate of 60 kilometers per hour. Okay, so if I give this a variable, this length, this distance traveled between the car and the intersection, I can call it x. So the rate at which x is changing with respect to time is 60 kilometers per hour. Okay. Also, we have a truck that is traveling away from the intersection, so it's going east. So here's my truck right here, okay, and it's just going away. Oh, so sorry about that. Okay, so it's going this way at a rate of 50 kilometers per hour. So if I give this a variable, I'm going to give it a variable of y. Okay, sorry, and this was x, just to clarify. dy dt is equal to 50 kilometers per hour. But one thing you always want to do is make sure your signs are correct. Notice the car is moving towards the origin or the reference point. Okay? The truck, however, is moving away. So if it's moving away from an origin, then it's going to be positive. The rate of change is going to be positive. If I'm moving towards the origin, it's going to be negative. So this value is actually getting smaller while this value is getting bigger. So if I draw a little bit of a snapshot here, as this is increasing, and this is decreasing, I'm going to have a triangle that looks something like this. So it's going to be a right angle triangle, and we want to find at what rate is this changing, the height, you see this length right here, what rate is this length changing with respect to time? And if I give it a variable, I'll call it z. So dz or dz dt, that's what we're trying to find, okay? Now, we're trying to find this value, however, at two very important points. When the car is 3 kilometers south of the intersection and when the truck is 4 kilometers east. So just keep that in mind. Okay, so let's start off by going with a formula here. Okay, so step 2 is find a formula that relates all these dimensions together. Since we're working with a right angled triangle, we're trying to find a distance of the hypotenuse. We're going to use the Pythagorean theorem. So z squared is equal to, t, is equal to x squared, which is the distance of the car from the intersection, plus the value of y squared, which is the distance of the truck away from the intersection. Okay, so at step 3, you want to substitute anything that's fixed. But, however, nothing with respect to this diagram is fixed. This is always changing. Okay, this is changing as well. So the length of x, and also as x and y are changing, the length of dz, the length of z is also changing. Okay, so nothing is fixed for this example. So I'll just put that here. Nothing is fixed. We can't substitute anything in. Okay, so let's go to step 4 here, where we take the derivative with respect to time. Of course, we're going to do this implicitly. So for z squared, we're going to have 2z, right? And since we're doing this implicitly, we have to follow up with dz dt. Okay, is equal to, take the derivative of 2x, okay, x squared, which gives you 2x, which also follows up with dx dt because we're doing this implicitly with respect to time, plus y squared. So the derivative of y squared is going to give you 2y, and we follow up with dy dt because, of course, of that implicit differentiation. At this point, you want to substitute anything that is changing. Okay, so there's a lot of everything in this diagram is changing. So let's put in some values here. Okay, so if I work with, let's say, the right-hand side, just for now, and we'll go to the left-hand side in a bit here. 2 times the x value, okay, so the distance of the car. The distance of a car at this point should be 3 kilometers. Okay, dx dt, we have that value, which is negative 60 kilometers per hour, plus 2 times the y value, which is the distance of the truck. And the distance of the truck is, it says here, it is 4 kilometers east. Okay, so this is going to be 4. And then dy dt is the rate at which the truck is leaving the intersection, which you are given, again, which is 50 kilometers. You're going to put in 50. All right, now the left-hand side is a little more interesting. We got a 2, which we leave as a 2. However, we need the z value. Now, they don't tell you the value of z. However, you can find it, okay? So we know we want the distance at which they are increasing, okay? So we know it's increasing. However, we want to know the distance at which x is equal to 3. Okay, and y is equal to 4. Now we can find z by, again, applying the Pythagorean theorem. So I'm just going to do this down here. Z squared is equal to 3 squared plus 4 squared, which gives me 9 plus 16. Okay, so z squared is equal to this, not the square root yet, 25. Therefore, z is equal to 5. So the point at which x is equal to 3 and y is equal to 4, z is equal to 5. Okay, so we're going to go back to my formula in step 4. So 2 times 5, and dz dt, that's exactly what we're trying to find. So we're just going to leave it as is. So remember, we need to isolate dz dt, the rate at which the distance between them is increasing. So let's clean up the right-hand side here. We have 2 times the 3 times the negative 60, which is going to give you a negative 360. And then plus 2 times 4 times the 50, which is going to give you 400. Okay, on the left-hand side here, I'm going to have 10 times dz dt. Okay, so let's continue cleaning this up here. Negative 360 plus 400 is going to give you 40. Okay, 40 is, oh, you know what, let me rewrite this. 40. Okay, 10 times dz dt. Okay, finally, as you can see, we are almost there. dz dt. If I get rid of the 10, I divide it on both sides. So therefore, the rate at which the z is increasing with respect to time is going to give me 4. But if we're working with the proper units here, we were working with kilometers per hour. So that is the rate at which the distance between the truck and the car is increasing. And that's how you do that question.